Hi, good morning. Assalamualaikum. So today I would like to continue on our class. So we should have an online class. As instructed by the management. Okay. So what we have covered. For our courses. So we go through this one. So we have covered. Topic 3, mechanics of materials, electricity principle, we are covered. Now we are going to continue with plastic behavior of materials. So I hope that you can go through all your assignments, and then you can go submit to me. So today I would like to share with you the topic on plastic behavior of materials. So plastic behavior of materials, week 8. Alright. So the first, I will share with you these notes. What is engineering materials? What is engineering materials? Since the early days of evolution of mankind, the main distinguishing features between human beings and other mammals has been their ability to use and develop materials to satisfy our human requirements. So nowadays we use many types of material fashioned in many different ways to satisfy our requirement for housing, heating, furniture, clothes, transportation, entertainment, medical care, defense, and other all trappings of a modern civilized society. So most material doesn't exist in a pure shape. It always exists as a ore. During the present century of the scope of metallurgical science has expanded enormously, so that subject can now be studied under the following headings. So covered, we have physical metallurgy, extraction metallurgy, and finally the process metallurgy. So you can go through on these notes. The selection of materials. So how to select the materials? For example, the metal joining piece and its clamping screws are made from brass. These metals has been chosen because its special properties. These properties are good electrical conductivity, ease of extruding to shape, ease of machining, for example cutting to length, drilling and tapping the screw threads, adequate strength and corrosion resistance. So the previous metal silver is an even better conductor, but it will be far too expensive for this application, and it will be too weak and soft, right? So another example, as in figure 2, shows the connecting rod of a motor and car engine. This made from a special steel alloy. This alloy has been chosen because it combines the properties of strength and toughness with the ability to be readily forged to shape and finished by machining. So when you want to select a material to develop engine, for example motor car engine, and then you can select these alloy materials. So those the reasons for selecting the materials in the above examples can be summarized as: first is due to commercial factors such as cost, ability, ease of manufacturers. And then second is engineering properties of materials such as electrical conductivity, strength, toughness, ease of forming by extrusion, forging and casting, machinability and corrosion resistance. Right? So you can go through on this. Almost every substance known to man found in a way into engineering workshop at some time or others. And then the most convenient way to study the properties and use of engineering material is classify them into families as shown in figure. So you can see this engineering material consists of metals and also non-metallic materials. Metal consists of ferrous metals and non-ferrous metals, and then non-metallic materials consists of synthetic materials and natural materials. So you can go through on this. What is metal? Consists of ferrous metals. Ferrous metals, there are metals and alloy containing a high proportion of element iron. And then example, ferrous metals such as bridge, building, the structure of large building, railway lines, locomotive, roll lock and bodies, and highly stressed engine parts of road vehicles. Yeah. So classification of ferrous materials. Ferrous metals consists of steel, cast iron, and wrought iron. Steel consists of carbon steel low, carbon steel medium, carbon steel high, and alloy steel. Yeah. And then cast iron consists of grey cast iron, white cast iron, malleable cast iron, high duty cast iron, and alloy cast iron. Yeah. So for non-ferrous metals consists of metal and also alloy. Yeah. For metal we have aluminium, cadmium, chromium, cobalt, copper, gold, lead, magnesium, manganese, molybdenum, nickel, platinum, silver, titanium, tungsten, and vanadium, and zinc. For alloy consists of brass, tin bronze, aluminium bronze, copper nickel alloys, aluminium alloys, magnesium alloy, zinc beam die casting alloy, and tin lead alloys. So for non-metallic materials consists of plastic. Non-metallic material consists of non-metallic, synthetic materials, and non-metallic. This is synthetic material consists of plastic. We have a thermoplastic and also thermosetting. For thermoplastic we have acrylic, PTFE, polytyrene, polynickel chloride, nylon, polystyrene. Yeah. For thermosetting we have epoxidite, acrylic, phenol formaldehyde, and formaldehyde, and urea formaldehyde. Yeah. So for ceramic consists of glass, porcelain, cemented carbides. Yeah. And then finally composite consists of carbon fiber, concrete, glass reinforced plastic. Yeah. So you just read all of these notes, and then finally for natural materials consists of asbestos, colorants, consists of dyes and pigments, coal, cotton, diamond, emery, gases consists of argon, methane, neon, nitrogen, oxygen, helium. And then you have glues, gums, granite, mica, oil, quartz, rubber, spire, wood, and wool. Yeah. So what is effective material properties? Yeah, consists of heat treatment. Yeah, the processing for this. Yeah, examples of hot working. Yeah, hot working, and B, cold working process. Yeah, and then environmental reaction. Consisting of rusting of steel, dissipation of brass, degradation of plastic. Right. So number 2, metal structure bonding materials. We have atoms, nucleus, electron, neutron. Yeah. So we have ions, consists of positive ion and negative ion. Yeah. This is the simple models of atomic structure for several elements. Yeah. For example, A or hydrogen, B helium, C fluorine, D neon, and also finally sodium. Yeah. So maximum numbers of electron in orbit 2 and 2n squared, where n identifies the orbit with n equal to 1 closer to the nucleus. Yeah. So this is the figure 2. The sodium fluoride molecule formed by the transfer of the extra electron of the sodium atom to complete the outer orbit of the fluorine atom. Yeah. So bonding, what is bonding in material? We have ionic bond. Yeah. Whereby we have a positive ion go to metallic ion negative. Okay. So for example, the sodium chloride is a most common example because of the transfer of electron between the atoms. Sodium and chlorine's ions are shown in this reaction. Yeah? And A and plus chlorine is equal to natrium chloride. Yeah. And then as number 2, we have a covalent bond. Yeah, this is a covalent bond. And then for example, covalent bond in molecule of methane, CH4. And number 2, a chemist express the structure formula of metal molecule. Alright. So for metallic bond, yeah, so we have a positive ion. Yeah. And then the dynamic representation of the metallic bond. This is the representation of the metallic bond. Yeah. And then finally we have a van der Waals force. Yeah. So for crystalline structure, yeah, so consists of body-centric cubics, face-centered cubic, and also hexagonal closed pack. Yeah, you can see the three principles of structure, which metallic element crystalline, A body centered cubic, B face centered cubic, and C hexagonal closed packs. So there are some metals that undergo a change of structure at different temperature. Iron metal, for example, is arranged body in BCC at room temperature. When the metal is heated and reach of 910 degrees Celsius, the atom rearrange themselves into a FCC or a crystal. If the metal is heated to the still high temperature of 1400 degrees Celsius, atoms again rearrange themselves this time into the BCC. Yeah, so this is the structure of that lah, right? So you can go through on this. This is the crystalline state. As we mentioned before that all the metals and its alloys have crystalline structure where the atoms are rearranged in organized shape, which is called as crystal lattice. This lattice is considered as another smallest grouping of atom. Each one is called the unit cell. Yeah, for example, this is unit cell for the this one, right? So the atoms that belongs to the unit cells are called the basic atoms. Its numbers different from one shape of arrangement to another. These numbers can be found from the following equation. N is number of basic atom in the unit cell. Nc is number of atom in the corner. Ni is the number of atom inside the structure. And Nf is the number of atom in center of the face. Yeah. So you can go through on this. Okay, this is the formula how you get for the figure 10. Yeah, the body centered cubic. How to calculate on this? Yeah, you have a V, and then you have the APF. APF for this is 0.68. Right? Okay, for FCC, yeah, for FCC, this is the formula for that, and then it's up to it will be 0.74 for hexagonal closed pack. Yeah, this is a formula. You can get a 0.74. Yeah. So example, the atomic radius of iron atom is 1.238 times 10 minus 10 meter. Iron crystallized as BCC. Calculate the lattice parameter of the unit cell. How many atoms are contained within the unit cell, and also find the atomic packing for factor. Yeah, and then using this formula, you have A is equal to 4 divided by 3 apostrophe 2 apostrophe 3 and times up, right? So you have this 2.861 times 10 minus 10 meter. Alright, and then the answer is 0.68, right? So then you go through on the topic 3, general properties of engineering material, physical property of materials. Yeah, what is density? Density is mass divided by volume, and then you can go through electrical conductivity. Yeah, so this is a plastic insulation coupled with conductor. Yeah. So for engineers, when we want to select the materials, we want to ensure that safety is the must. So and then this is the things that you need to select a good conductor materials. Yeah, and then you need to consider about the melting temperature of materials, and then also semiconductor. So for thermal conductivity, this ability of material to transmit heat energy by conduction. Yeah, and then figure 2 shows a soldering iron. The bit is made from the copper, which is a good conductor of heat, and so we allow the heat energy stored in its travel easily down to the tip into the work being soldered. Yeah, so wouldn't that remain as good as low thermal conductivity, and this is the flow heat of energy, right? And then this is the fusibility, yeah, possibility, reluctance, and temperature stability. Yeah. So what are the mechanical properties of material? It consists of tensile strength. Yeah. So this is the test to get the tensile strength for this metal. Yeah. For the strength is the ability of material to resist applied forces without fracturing. Right. So what is toughness? The ability of material to withstand bending, or it is application of shear stresses without fracture. Yeah. So the rubber and most plastic material do not shatter. Therefore, they are tough. Yeah, for example, if a rod made of iron carbon, studied, it will be bent without breaking under the impact of the hammer. while if a rod is made of glass, it will broken by impact loading as shown in figure 5. So number 3 is malleability. Number 4 is hardness, right? Ductility, stiffness, stiffness, brittleness, elasticity, plasticity. So there's the parts. That's for those chapter. Okay, so then you can continue with the material testing. So you can go through on this tensile. What is the tensile test? Tensile styles using this tensile testing machines. So then it is the sample for the test. So okay, so this is the elongation is equal to applied force times L. L is the length divided by E, elastic modules, times A, the cross-sectional area. Okay, so tensile test result should be a load extension curve for low carbon steel versus the forces, and then you can see this from A to B. The extension is proportional to the applied load. Also, for the load is removed, the specimen returns to original length. Under this relatively light loaded condition, the message showing elastic properties. For this region is elastic properties lah, right? So for the BC, B and C, it can be seen from the graph that is the metal suddenly extend with no increase in load. If the load is removed at this point, the metal will not spring back to original length and is said to have taken a permanent set. Therefore, B is a core limit of proportionality. And if the force is increased beyond this point, a stage is reached where a sudden extension takes place is no increase in force. Those is known as the yield point of C. So stress is the stress at the yield point, that is the load at B divided by the original cross section of the specimen. Usually a designer works at 50% of the figure to allow a factor of safety. From the C to D, the extension no longer proportional to the load, and if the load is removed, little or no spring back will occur. Under this relativity, greater loads, the metal is showing plastic properties, right? So it will not go back to the condition. And then for the point D is the referred to the ultimate tensile strength when referred extension of the limit stress when referred to a stress strain graph. The ultimate stress is calculated by dividing load at D by the original cross section. Although it is useful the figure of comparing relative strength of material, it has little practical value since the equipment is not usually operated. So this is the stress is equal to load divided by area cross section divided strain equal to extension divided by original length. So the sensor is preparing result on some materials. You can see this. Alright, so you go through on this topic. Okay, and then therefore the stress divided by strain is equal to E. E is known as a Young modulus, and then the modulus of elasticity or the tensile modulus, those E equal to tensile compression stress divided by strain. Alright. Okay, so for example, calculate the modulus of electricity for material which produce the followed data when undergoing test. So applied load is 35.7 kN, cross section area is 25 mm squared, gauge length is 28 mm, extension 0.2 meter. So E is equal to stress divided by strain, where stress is equal to 35.7 divided by 25 is equal to 1.428 megapascal, and also strain is equal to 0.2 divided by 28 millimeter is equivalent to 0.007. So therefore E is 35.7 times 28 divided by 25 times 0.2, 1 equal to then 199.92 or 200 gigapascal approximately, right? So this is how the test conducted, and then you can get the E. So for the compression test, you can see the compression test for this, and then we have a telltale testing, that is testing, impact testing, and then also this is the test conducted. Okay, and then we have a grip test, hardness testing, repeated hardness test. Okay, Vickers Estes test, the Rockwell hardness test, a Shaw scroll scope. Yeah. Then go to another topic, surface hardening steels. Yeah, there are 4 main types of surface hardening, which are case hardening, needling, flame hardening, and induction hardening. Yeah. So what is case hardening? You can see this case hardening. Case hardening A carburizing, B after carburizing, C after quenching component. Yeah. Second, first is carburizing. Carburizing make use of a fact that the carbon steel absorb when heated to austenitic conditions, whereas carbonous metals are used in carburizing process as follows. Yeah? So we have a carburizing in solid media. Okay, carburizing in liquid bed, and carburizing of gaseous media. And then we have a heat treatment at carburizing. So we have austenite, austenite ferrite, ferrite apatite, and so on. Right? So you can go through this topic, flame hardening, induction hardening. Yeah. So for equilibrium diagram, so we have a few phases. For this, the possible phases is water vapor, steam, liquid salt solution, crystals of water, and also crystal of salt. Yeah. So alloying system, there are many types of alloyings which are binary system. It means they have 2 metals only, ternary system and the multi system. Alright. Okay, so you can see the phase equilibrium diagram for this. Yeah, solid A plus B, solid B plus liquid AB, and so on lah. Alright. So okay, so you can go through on this. This is from the various materials subject lah, right? So we have critical temperature. Yeah. Number 7 is heat treatment of carbon steels. We have annealing, normalizing, hardening, and tempering. Right. So you can see from this equilibrium diagram. Yeah. So heat treatment temperature range of classes of carbon steel in relation to the equilibrium diagram. So what is annealing? All annealing process. There are 3 basic: stress relief annealing, spodizing annealing, and also fuel annealing. Yeah. So you can go through on this lah. Right. Okay. Normalizing, hardening, tempering. So this one is cast iron. What is cast iron? Yeah, you can see for this cast iron, the phase diagram of the iron. Yeah, from this, yeah, you can see. Right. Okay. So number 9 is the alloy steel. Yeah, what is alloy steel? Yeah, you can go through on this. What is alloy steel? Alright. And then what is metal cutting? Metal cutting is how the principle of oxy-fuel gas cutting. Yeah. So how they cut the material, right? So for non-ferrous materials, one is alloy and is alloy. Yeah. Okay. Next, copper on is alloy. What is copper and an alloy? And the exact quantity of copper. Yeah. This is a topic to assist you in future when you want to select materials for your components. Yeah. When you want to design something, then suddenly you want to choose what material is suitable for the purpose. Yeah. So you can go through on this lah. Alright. So the 12 is polymer and plastic. Yeah, what is polymer and what is a plastic? Yeah, so you can go through on this. Yeah, it's more towards a chemical bonding. Okay. Alright. So number 13 is corrosion and its prevention. So how you want to get protected from corrosion. Yeah. So the three factors govern corrosions. First, the metal from which the component is made, the protective treatment and the component surface received, and then finally the environment in which the component is kept. Yeah, so we have a dry corrosion, wet corrosion, and galvanic corrosions, right? So atmospheric corrosion, we have a galvanic corrosion. Yeah. So when we have a sodium electrode, for this is minus 2.71, magnesium minus 2.4. Yeah. So which is the best materials? The best is gold plus 0.5, 1.5. Yeah, protected is alright. Also silver also good. Copper is also good. Alright. So corrosion is rated by mechanical stress, and then we have a corrosion fatigue, corrosion, impairment corrosion. Yeah. So factor affecting corrosion, the structure of the design. So when you want to design something, so make sure that your design is not impacted toward the design lah. And then consists of environment. Yeah. For example, when you do in the production near the sea, and maybe your components easily be corroded. Yeah. So apply of internal stress, corrosion of structure, and also the temperature. Yeah. So how we want to protect all the corrosions? Yeah. First, the use of a metal or alloy which element corrosions resistant. Right? Okay. Alright. You go through on this. And last is number 14 is ceramic. Foreman construct the army of ceramic materials, scissors, a china teacup, a building bridge, a floor tiles, and a glass vase. Right? Okay. Mechanical properties. Yeah, so consists of little structure of ceramic, a stress strain behavior, hardness. Yeah. So type of applications of ceramic. Ceramic materials consist of glasses, clay product, refractory, abrasive, cements, advanced ceramic. Yeah. So what is the glass? Glass ceramic material have been designed to have double following characteristic relative to high mechanical strength, low coefficient of thermal expansion, relatively high temperature, and also good biological compatibility. Yeah. So we have a clay products, refractory, abrasive, cements, advanced ceramic. So number 15 is the deformation in metals. After studying the mechanical properties of material, we learn that deformation can occur either by elastic movement or by plastic flow. Yeah. So elastic flow in metals, plastic flow in metals. Yeah. Slip. Okay. Alright. This more towards reading, so you can go through on this. Yeah. The industrial shaping of metals. Metals and elements be shaped into something approaching the final required from by one the following operations: casting into either a sand or metal mold, casting in ingot followed by a hard working process, casting ingot followed, and also sintering from powdered metal. Right? Okay. Okay, you go through on this. Yeah. So if you go through, you can read this one, and then number 17 is composite materials. What is laminate composite? What is a plywood? Okay, this is sandwich planes. Yeah, it's more towards this one. Alright. Number 18 is wire welding. There are many types of joining materials and dialogue, which are soft soldering, brazing, and welding. There are two types of welding: fusion welding process and solid base welding process. Yeah. Okay. Number 19 is modes of failure analysis. Available working stress, failures of material in service. Yeah. So this the thing. Okay. Okay. So when you go through all this, and then after you complete reading this, you can submit your tutorials that have been submitted to you. Yeah. So okay. So you also can see what is the elastic and plastic deformation. I will share with you these videos what is elastic and plastic deformation.
In this video, we will cover plastic and elastic deformation. This includes definitions of plastic and elastic deformation, the position on the stress-strain diagram, and provide illustration of how several types of materials behave under both elastic and plastic deformation. Understanding plastic and elastic deformation is of key importance in material science and engineering because these principles determine how material forms under loading and unloading. Before we define elastic and plastic deformation, let's define stress and strain as they quantify deformation.
Okay, so you
Stress
can go through all
or
this.
stress.
Okay. So I will share with you this video for you to go through. Alright. So after you go through the topics that been covered, so you can go to tutorial 8. Tutorial 8. Okay, so we have a 5 marks for this out of 16 mark. This is for assignment 8. So discuss in detail what material suitable to use for this figure 1 and why. So you can just discuss on this lah, right? Number 2, discuss in detail what material suitable to be used for the figure 2 and why, for that car engine. And then number 3, fill in the box as shown in the below picture. So we have a 3, 1, 2, 3. So only 3 easily question, right? So if you seeing this video and then you can say yes, and then you can submit this tutorial by email to me, sukairul.razak@ctedu.com. So I think if you have any question or you want to talk with me, you can just call or WhatsApp me, or you can comment from this video, right? So that's all for today. If you have any thing to ask, you can call me directly. Alright, thank you, and again and please respond for your attendance, right? Okay, thank you. Assalamualaikum and good morning.